So welcome again to CH5010 chemical reactor theory. So we are now getting into modeling simulation of reactors. That's what we started in the previous lecture, and we had briefly done this right in the beginning of the course. So let me just go over the uh, outline from Davis and Davis's book. So we had looked at partly the reactors for while talking about measurement of reaction rate, as well as recapping the prior work in module 2 and 3. So that's when we had discussed a part of chapter 3, and the other part that would be relevant for you would be chapter 9, non-isothermal reactors, from Davis and Davis book. From Froment and Bischoff, the relevant chapters are going to be chapter 8, 9 and 10. 8 and 10 talk about the well mixed reactors, and chapter 9 talks about the plug flow reactor. Okay. So please go over those materials. We are not going to go over each and every nitty gritty details, but we will generally talk about how we are going to solve the overall reaction models. Okay. So just to recap the reaction, the balances that we have. So the balances that we have are the species balance, okay, this is the overall species balance, and overall energy balance is okay. So these are the two balances when we are talking about, or plus maybe if there is heat transfer, then area of heat transfer multiplied by the flux of heat transfer, right. So this is the overall balance equations that we have. When we are talking about batch reactors, we do not have these terms because there is no in and out from a batch reactor. Okay. So this is essentially what we get when we are talking about batch reactors. Okay. So that's what is basically written over here, and you might need certain other assumptions in order to solve these equations. Okay. Oftentimes when you have solved the kind of problems that you solved in your undergraduate, the type of problems that you solved usually would have involved one single reaction when it came to non-isothermal system. So if there is just one single reaction, I'll just okay, if only one reaction, then you are going to or let us say just Kca to the power alpha. Let us just write it in this particular form. Okay. And you will have V rho Cp dt by dt equal to V multiplied by minus delta H Kca to the power alpha. Okay. This is essentially what you are going to have over here. Okay, and if you see this particular guy, this is nothing but this, right. So you will be able to plus QA. So you will be able to write this as V rho Cp dt by dt equal to minus V dCA by dt plus QA if it is non-isothermal. Okay. So essentially, if there is only one reaction, you can get rid of temperature, okay, by converting it in terms of concentrations. Okay. And essentially what you are going to get is T and because of this you are going to get an equation of the nature T is going to be equal to Tn plus delta T adiabatic multiplied by conversion if there is no heat transfer. If there is heat transfer, then you will have QA from heat transfer as well. Okay. So this is the kind of form that you will expect to get. Okay. Don't necessarily follow the derivation, it's there in the next few slides. Okay. So this is how we actually try to solve those non-isothermal cases. If it's isothermal, you don't have the dt by dt term at all, you just have dc by dt terms. Okay. And that's the way you can solve. Okay. So you have lot of these complications that can potentially come into the overall problem that you are trying to solve. Okay. All of those cases, what you need to do is you need to write down those equations for each individual species and then try to use some of the concepts in order to convert multiple equations in multiple unknowns into one equation in one unknown, or simultaneously solve two equations in two unknowns. That is the kind of approach that you will do if you are solving with pen and paper, as you might, or at least some of you might do next semester. If you are solving this by numerically, you do not have to go through any of these hoops, you can directly feed it to a numerical solver, and how to do that we will take that case in the next semester's course. Okay. So do not worry about the derivation over here, we will go over various cases. So let us, before now, if this is isothermal, you do not need to solve this equation. Okay. Instead you are going to get the case where temperature is somehow maintained constant. That is an example that you had already done in the semi batch reactor context in first assignment. Okay. Okay. So now let us say we were to consider HBr synthesis example. Okay. What is the equation that you are going to use if we are going to do HBr synthesis? So the reaction is this is carried out in, let us say, a batch reactor. Okay. Now first of all, here because there are 2 moles on the left hand side, 2 moles on the right hand side, there is no volume change happening because of the reaction, and therefore you do not have to worry about the volume change aspects. Okay. Now if you wanted to solve this reaction, this example, how would you go about doing it? Just think about that. Give yourself a minute or two to think about. Did you guys get time to read ahead at all over the weekend? No? 3 days you had, no? You have to spend too much time reading. Half an hour would have been really sufficient. Okay. Following the course a little bit tough and all that, those questions will not come that strongly if we do read ahead a bit. Okay. Yeah. Okay. So essentially the way we will solve any problem like this is there are 3 species, so you can write up to 3 equations. Okay. So, we have said that this is batch reactor and isothermal. So, we will have V dCH2 by dt or V and V will get cancelled. Okay. So, you are basically going to have dCH2 by dt equal to minus R dCBr2 is minus R is 2R. Where does 2 come from? Because of the stoichiometry, right. So, these are the 3 equations. The question is that do you actually need 3 equations? Okay. You do not really need 3 equations because the stoichiometry freezes how H2 and Br2 change. Okay. So, you can very well stick with this. Now, okay, if you want to do it using your chemical reaction engineering or chemical engineering fundas, okay. So, if n moles of CH2 if XH2 is the conversion of hydrogen, okay, then CH2 is going to be equal to CH2 initial or right multiplied by 1 minus XH2, right. Likewise, CBr2 is going to be CBr2 initial, not in, sorry, minus, okay, okay. So, you can do that, and when you plug into any of these equations, you will see that you have converted 3 equations in 3 unknowns into one single equation in one unknown. Okay. You can use any of these equations and you will get the same result. Okay. So, that is approach number 1. Approach number 2, if you were to do this, you will have again okay. So, from this you will get is dCH2 by dt equal to dCBr2 by dt. You just integrate it and you will get CH2 minus CH2 naught okay, and which will essentially give you CBr2 at any time is nothing but and if you look at this particular definition, that is exactly what you have over here. This term is nothing but CH2 0 multiplied by XH2, which is essentially what we had written over there. Okay. So, now again you can convert your 2 equations in 2 unknowns into one single equation in a single unknown, right. Okay. So, either method that you want to use, you are free to use either of those methods and you will end up having the same equations, and that is what the next slide shows, right. So, your basically based on your chemical engineering fundas, if you were to do the overall mass balance and do those manipulations, you will get basically an equation of this sort. Now, what is this equation? This is nothing but substituting the rate of reaction, this rate that we have over here, we just substitute the values in terms of x, that is conversion. What if we were to use this particular approach? If we were to use this particular approach, again we can substitute those, okay. And if you do the math just by plugging in what does CH2, how is CH2 related to XH2, you will see that this and this are exactly equivalent, okay. So, now you can solve either of these equations and you will get, how conversion of hydrogen varies with time or how concentration of hydrogen varies with time, okay. For the most part, I think in your undergraduate this is the method that you might have used, okay. Whichever one you want to use, we are very much free to use that, okay. What if it is a non-isothermal reaction, okay. If it is a non-isothermal reaction, again I said that it is one single reaction, okay. So, what you are going to get is dt by dt is going to be basically in this form, okay. And when you substitute that, you are essentially going to get, so what you are going to get is this is if you have 1 mole of hydrogen is being consumed, but instead if you have these many number of moles of hydrogen being consumed, this is going to be your temperature, okay. This is essentially equivalent to what we were trying to show in over here, okay. Alternatively, if you are going to do algebraic manipulations, you are going to get dt by dt is of this sort, okay. And R, as we had said, R is nothing but dC by dt, dCA by dt, okay. So, if you substitute that over here, you get the equation in this one. Okay. This particular guy, I think I had missed that part here. Oh, not VDC by dt, sorry. Sorry, not, I had missed the delta H over there, okay. So, if you are to divide this by V rho Cp, you will get dt by dt equal to minus delta H by rho Cp, which is what you see over here, minus delta H by rho Cp, and if you have minus delta H by rho Cp, this is your delta T adiabatic, okay. And this is, if you see, this and this expression are exactly the same, okay. This is what you get if we are trying to solve batch reactor, okay. Now, batch reactor is going to be a little bit tougher than CSTR. Why? Batch reactor will involve differential equations. We will do a batch reactor example tomorrow, okay. Today we will do a CSTR example, okay. Okay, so I will leave this over for you, whichever method you are comfortable with, perhaps the conversion based approach if you are comfortable, so be it. You can take a look at it, spend your time thinking about it. We will directly take an example next, okay. And then we will see whether or not you are able to solve it, okay. So, yeah, I will take the attendance, which will give you maybe a few minutes to look at this slides and hopefully recall some of the things that you have done in your undergrad if you are a chemical engineer. If you are not a chemical engineer, just take some time to digest what we have said over the last 20 minutes. So, just put an example which is a problem in Davis and Davis to do this in CSTR. So, that is uploaded on the course website. We will try to solve this problem so that you have one more example in addition to the ones that are there over here. Okay. So, just the way we had done earlier, we will have a steady state species balance, we will have a steady state energy balance, okay. And if you have these two equations, you are basically trying to get rid of some of the terms to obtain temperature in terms of concentrations, so that you can then substitute and solve, okay. So, that is the overall idea. So, what you can do over here is basically see that RV is nothing but Q multiplied by Ca naught minus Ca. So, Q multiplied by Ca naught minus Ca can be substituted over here, okay. So, then you divide by Q rho Cp. If you divide by Q rho Cp, you are basically going to get an equation which looks very similar to the equation that we did last time, okay. What will the equation look like? T is going to be nothing but T naught plus adiabatic rise in temperature multiplied by conversion, okay. So, that is again for CSTR also the kind of equation that you are going to get, okay. So, this is basically T equal to T naught plus adiabatic rise in temperature multiplied by conversion, okay, plus any loss of heat to the surroundings or because of any heat transfer medium, okay. That is essentially what you are going to get, and once you substitute and solve, you will be able to find the final, you will be able to solve the final equation, okay. So, this is the kind of equation that is there. So, if it is a problem of simulation, that means you are given volume of reactor, you are given the inlet flow rate, you are given the inlet conditions, okay, and you are supposed to find out what the conversion and temperature is going to be. Design problem on the other hand, okay, is find out the volume of the CSTR so that you will get conversion of 75%, okay. The reason why a lot of examples in your, this sounds familiar to from undergraduate, okay. The reason why a lot of problems in your undergraduate are formulated in this form is because for CSTRs it's fairly easy to calculate it using this approach, okay, compared to if we are going to ask you what is going to be the conversion and temperature, okay. So, this is an example where the question that is given your K naught, given your C, your V, your initial inlet concentration, okay, obtain the reactor volume that will give you the desired conversion, okay. So, again I think this is unfortunate, I should have used okay. So, this is a problem that we will try to solve now. So, this is the problem that we are going to solve. So, there is one single reaction A going to products. So, we basically need to do a balance on A. Okay. And we also need to do energy balance because this is non-isothermal. Okay. So, because it is CSTR, this is what we have. Okay, this is going to be nothing but okay, this is going to be a balance. Okay. If you notice, basically RV term is basically this guy. Okay, and this, if you basically take it onto this side, this term is nothing but Q multiplied by Ca in multiplied by C minus Ca. Now further, if you divide by okay. So this is what you have. So you now have basically two equations and two unknowns. Okay, and this or this can be written as Okay. So, where our K is okay, where T itself is this guy. Okay. So, all you have to do now is to substitute the values, right. So, in this particular problem you have 0 equal to Ca in is 5 moles per liter, minus delta H is 70. So, T in rho is 1000 meter, Cp is 4 kilojoule per kg. Okay. Ca in, so we have this Ca in is 5 moles per liter, okay, which is basically 5000 moles per meter cube. Okay, and 1 minus Ca minus Ca in. Okay, so this is what you are going to get, 1000 moles, kilojoules, kg, meter cube, 5, and this Kelvin goes up. Okay, so you have 70 multiplied by 5 divided by 4, 3500, sorry 350 divided by 4, 1 minus okay. So now you can just kind of try to substitute this in the other equation and then try to solve it. Okay. So that's the way that we can solve Ca and we can just write this as 5. Okay. So if the question is given tau, Okay, these are two different problems. Okay, if you want to solve this, you will have to solve a nonlinear equation. If you have to solve this is a substitution problem. Okay. So, this problem has, I think, two parts. Is given Tn equal to 300, okay, given Tn equal to 300, what is going to be the conversion? That is the question. The other question is that given T out equal to 350, so we can substitute T out over here to be 350. Okay, we have our tau, and from there we can easily calculate our Ca. Okay, so this is the first question. Let me write. Okay, you have to solve for the first question. You have to solve these two equations. Okay, they are not exactly two equations, it is just one equation. The second one, T equal to 300 plus 350 by 4 multiplied by 1 minus Ca divided by 5, we can directly substitute it in over here, right, and get the result. Okay. Alternatively, you can write Ca in terms of temperature and then substitute Ca by 5 in the second equation. Whichever way you do, in one case you will be solving for Ca, in another case you will be solving for T, and it is a non-linear equation and one unknown that you can solve. Okay. A similar problem you are going to have in your assignment. Okay. The second question, was okay, if T equal to 350, then from the second equation we have okay. So if you take a look at this, you are going to get CA equal to CA in this is going to be a CA, okay, and you substitute this CA over here, you will get the value of your QA. Okay. So, this is how you will solve the second question over there. Okay. Yeah. Sorry? Could be. Yeah. I am not sure. This guy? Yeah. Maybe. Q rho CP. Yeah. Thank you. Okay. So, it is not the final answer and so on that matters. Okay. It is kind of the understanding and the procedure that you need to follow that matters. Okay. So, yes, we have gone very quickly, that is true, but all of these problems are solved problems in your book, and that is something that you can take your time and learn it from the book. I can actually spend 4 days doing this derivation, you are not going to get anything. I mean, we are optimizing in our education system, we optimize for instructions, we are not optimizing for learning. Learning happens when you try to solve the problems yourselves. Okay. So, we have two assignment problems. We have this example. Okay. So, try to solve this example and try to start with your assignment problem for your CSTR. Tedious things, these are not really difficult things. Okay. You have all the tools that you require in order to solve these problems. These are not new tools as such compared to where we started this semester. Okay, we have gone over all of these solution approaches. Okay. All right. So, thank you, and we will see you tomorrow.